I want to welcome you to Lecture 21, Unit 4. This is Applications of Normal Distribution. My name is Jorge. So for this lecture, we have two objectives. We're going to find the probabilities for a normally distributed variable by transforming it into a standard normal variable. And then we're going to find specific data values for giving percentages using the standard normal distribution. So the standard normal distribution can be used to solve a wide variety of problems. And the only requirement is that the variable that we're looking at it has to be normally distributed or approximately normally distributed. Now, to solve these problems, what we do is we simply transform the variable into standard normal variable, in other words, a z-score. And the formula that we use is x minus mu divided by sigma. So here's an example. The scores for a standardized test are normally distributed. We have a mean of 100 and a standard deviation of 15. When the scores are transformed to z values, the two distributions coincide. So here we have the raw data, right? So the mean is 100, standard deviation of 15. So one standard deviation above the mean will be 115. If I standardize it, my mean becomes 0, and then my 15 just becomes a 1. So 100 corresponds to 0, 115 corresponds to 1, 85, which is one standard deviation below the mean, is a -1, and so on. So you can see how the two actually coincide. So here's an example. Consider the intelligence quotient, IQ scores for people. IQ scores are normally distributed with a mean of 100 and a standard deviation of 10. If a person is picked at random, what is the probability that his or her IQ is between 100 and 120? In other words, what we're looking for is what's the probability that a randomly selected person will have an IQ score of between 100 and 120. And then we're going to find the probability that a person selected at random will have an IQ greater than 90. So first, I'm going to go ahead and do this using z-score. So if I convert these two values to z values, I get a value of 0 for 100 and a value of 2 for 120. And then I can use the distribution tables to find this information. So I'm going to show you how to do this using the website. So I converted everything to standard normal distribution. Excuse me. So 0 and 1, and I'm looking for between 0 and 2. And you can see that I get the 0.4772. Now, I can also do this without having to convert it into z-score. So standard deviation, my mean was 100, standard deviation was 10, and it's between 100 and 120. So this website has the ability to do either or. And you can see that I get the same answer, which is about 47 to 48%. Okay, so now, the next thing is find the probability that a person selected at random will have an IQ greater than 90. Well, an IQ greater than a score of 90 gives us a z-score of -1. So using the website without converting it, I'm looking for above 90. And when I do that, I get 0.8413. So about 84% chance that a randomly chosen person will have an IQ score greater than 90. Now, if I convert it if I standardize it, then I'm looking for above -1, and I should get the same answer, and I do, which is 0.8413. Okay, so the next thing is a survey found that women spend on average $146.21 on beauty products during the summer months. Assume the standard deviation is $29.44. Find the percentage of women who spend less than $160. Assume that the variable is normally distributed. So this is the assumption that we have to make, that the variable that we're looking at right now is in fact normally distributed. So here we have the information. So our z-score is 0.47. So I'm looking for the probability that the z-score is below 0.47. So it's going to be below 0.47. And doing that, I get an answer of about 68%. Now, if I go back and I use this information that I have here, I can actually do it without having to transform it. So this becomes 146.21. This becomes 29.44. And I'm looking for spending below 160. And I get the same information, which is 0.6803. So either method will get you the answer that you're looking for. So here's another example. Each month, an American household generates an average of 28 pounds of newspaper for garbage or recycling. Now, assume the standard deviation is 2 pounds. If the household is selected at random, find the probability of it's generating between 27 and 31 pounds. and more than 30.2 pounds. The other assumption is that it is in fact normally distributed or approximately normally distributed. So let's go ahead and find it using the Z-scores, right? So here are the two ways. So if I convert 27 to a Z-score, I get negative 0.5. If I convert 31 to a Z-score, I get 1.5. And so I add up those two probabilities and I get 62.47%, about 62.5%. And then more than 30.2 pounds gives me about 13.6%. So either way will get you the correct answer, but I'm going to show you how to do it using the website. So my mean is 28. So here is my mean is going to be 28. My standard deviation is going to be 2. And I'm looking for between 27 and 31. So I'm going to go ahead and just type in those values there. And I get 0.6247, which is 62.5%, which is exactly what we got you doing it the other way. Now the other one was greater than 30.2. So I'm going to do above and I'll put 30.2. So what's the probability that a family recycles more than 30.2 pounds of newspaper per month? And I get about 13.6%. So again, either way will get you the correct answer. All right, so let's go back here. The next thing is finding data values giving specific probabilities. So the formula for finding X. So if you know what the Z-score is, if you know what sigma is, if you know what mu is, you can actually find the specific X. So here's an example. In a large class, suppose that your instructor tells you that you need to obtain a grade in the top 10% of your class to get an A in a particular exam. From past experience, she is able to estimate that the mean and standard deviation of this exam will be 72 and 13 respectively. What will be the minimum grade needed to obtain an A? Again, assume that the grades will be approximately normally distributed. So here's the formula, and this is how we get our answer, right? So for this example, you have to score, the minimum that you can get is an 88.67. But there's a piece of information that we're not sure how we got, which is this 1.282. How do we get this? Well, we're looking for the top 10%, which means that 90% is below. So using the website, I can get a value from an area, and this is going to be 0.9. And I want below, and I get 1.282, which is the Z-score that corresponds to a 90% probability. And then I use this information with the mu and the standard deviation to find the minimum score, which in this case was 88.67. So here's another example. For a medical study, a researcher wishes to select people in the middle 60% of the population based on blood pressure. If the mean systolic blood pressure is 120 and standard deviation is 8, find the upper and lower readings that will qualify people to participate in the study. So here we have the information, and this is what we end up with, right? We end up with, you have to have a blood pressure between 113 and 126. Well, how do we get that information? So I'm going to show you the two steps. The first thing is I'm going to show you that we can get these values without even having to find the Z-score that we're going to use. And then I'm going to show you how it is that we found the Z-score, right? So going back to the website, the mean is 120 with a standard deviation of 8, and I'm looking for, So here, let me do it this way. So 0.6, 120, standard deviation of 8, and I'm looking for between, and you can see that it actually gives me my values. It gives me 113.268 and 126.732. So you click on value from an area, you put the area that you're looking for, you put the mean, you put the standard deviation, click between, and it gives you the two parameters. Now, if I wanted to get the Z-score, the Z value, so here, how did I get the 0.84 and negative 0.84? Well, the way that we do that is instead of using the 120 and the 8, we use a 0 and the 1, and that gives us our Z-scores. So the Z-score that corresponds to 113 is negative 0.84. The one that corresponds to 126 is the 0.84. So the next thing that we're going to talk about is how do we determine normality? So a normally shaped, a bell-shaped distribution is only one of the many shapes that distribution can assume. So it's important since many statistical methods require that the distribution of values be normally or approximately normally shaped. And if it's not, then you can't use that whatever testing method that you're trying to use. Now, there's several ways that statisticians check for normality. And the easiest way is to draw a histogram for the data and check the shape. And if it looks like a bell curve, then we know that we're good to go. Now, if the histogram is not approximately bell shaped, then the data is not going to be normally distributed. The other way that we can determine normality is by checking skewness. And skewness can be checked by using Pearson's coefficient of skewness, also known as PC. And so the formula is 3 times x minus the median divided by s. Now, if the index is greater than or equal to +1 or less than or equal to -1, then it is significantly skewed and is not a normal distribution. So some notes on the Pearson coefficient skewness. There's actually 2 of them. Pearson's first skewness coefficient is 3 times x minus the mode, and the other one is 3 times x minus the median. So here we have a survey of 18 high technology firms that show the number of days inventory they had on hand. Now determine if the data are approximately normally distributed. And what we're going to use for this is actually an Excel file that I have here. And here's what it looks like. So here are the 18 days. And what I did was I actually found I did the class limits. And then I found the frequency. Now, you could have done it this way, or simply just done the average, which is what I did here. So, the average of this just turns out to be 79.5. The median is 77.5, with a standard deviation of 40.5. And so my Pearson coefficient, or my PC, is 0.14. So that tells me that this data is in fact approximately normally distributed. But before you even do all of this, you can see the histogram, and you can see that it does follow somewhat of a normal curve. And I'm sorry, I did this so I can graph it a histogram, but I actually used a straight mean. So you can see that it actually does look like a bell curve. So this histogram actually reinforces the Pearson coefficient. Okay, so the next data is the data shown consists of number of games played each year in the career of Baseball Hall of Famer Bill Mazeroski. And so we're going to determine if the data is in fact approximately normally distributed. And looking at the data here, so the first thing I'm doing is I'm going to go ahead and graph this in a histogram. And right off the bat, I can see that this is in fact not even closely normally distributed. But I want to double check it, right? So what I do is I find the Pearson coefficient. So I find the mean, I find the median, the standard deviation, and then I go ahead and find the coefficient, which is -1.18. And remember that if it's less than or equal to -1, then it's significantly skewed. And you can see that this is in fact significantly skewed. And that's the end of lecture 21, unit 4. Thank you.